So good evening all and welcome to session 3 of day 3. So we already have the expert for this session who has joined us. I would like to introduce the expert. Shri H.S. Kushwaha sir has joined the reactor engineering division in 1971 after graduating from the 14th batch of Baba Atomic Earth Sector Training School in Mechanical Engineering. He did his master's in mechanical engineering with specialization in finite element methods from IIT Kanpur. Since the beginning, he has been working in the area of structural mechanics and he has published more than 650 papers. I would now like to request Shri H.S. Kushwaha sir to kindly start with this session on static dynamics. Over to you.
Hello, good afternoon to everyone. We will start with a static analysis using FIST. So, Aniket, can I have the first slide?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Uh, okay. In the first slide, you see, just 1 minute. We have shown a spring which is clamped at the left side and attached to a mass on the right side. So instead of the mass, if I pull the spring which has a stiffness K, then the stiffness can be defined by the load which is applied divided by the displacement of the at the point of loading. So K is equal to, the stiffness is equal to P divided by delta. Delta is nothing but deflection at the point of application of the load. Now, if I write the equilibrium equation, and suppose if the point at the left side is not fixed, if it is allowed to move, then the entire equation can be written as minus Ku, which is nothing but at the point of fixing, the node is 1, at the other point is node 2, and the displacement at the node 1 is U1 and the displacement at the node 2 is U2. So this can be written as minus Ku minus Ku2 equal to P1, and by the equilibrium, by the total force, that is P1 plus P2 equal to 0, I can write P2 also, and P1, P2, P1 is the load applied at the node point 1 and P2 is the load applied at the node point 2. If we write down in the form of the matrix these two equations, then the equation will look like minus K, K, minus K, K, this is the matrix, 2 by 2 matrix, into displacement U1, U2 at the node 1 and 2, and the load P1, P2. So stiffness matrix multiplied by the displacement vector equal to the force vector. This. Now, this here, if we talk about the stiffness is defined by the load per unit length, whereas stiffness matrix for the same element is written as 2 by 1, because both the point 1 and 2 they can move on the right side. Okay, next, can we go to the second slide? Aniket, second slide. Okay, if I have a two
Yes.
element, and if they are connected in series, then we know that two spring, the equivalent stiffness of the spring can be written as 1 by Keq, which is nothing but the equivalent stiffness, equal to 1 by K1. K1 is the stiffness of first spring and K2 is the stiffness of the second spring. Now the same addition, this is now simply adding the two springs which are connected in series. If I can write down in matrix form, the same thing can be written as simply for the element 1 and 2, The common is node 2, therefore they get added K1, K2, and the stiffness will become K minus K1 0, minus K1 second row, K1 plus K2 minus K2 0, K2 third row, and K2. So this is the stiffness matrix of these two springs. There are some properties of the stiffness matrix that we know. The order of the stiffness matrix corresponds to total degree of freedom. Here the total degree of freedom is, we have a two element and three nodes, so 3 by 3. It is a singular matrix. Singular matrix means if I take the determinant, I will get 0. It is a symmetric matrix that the K1 plus K2, K2, they are it is a diagonal. About that, the matrix is symmetric. And diagonal term of the matrix is always positive. Okay, this is the fundamental properties of the whether the element stiffness matrix or global stiffness matrix. We call, when we come to the global stiffness matrix, it is the system matrix, stiffness matrix. Okay, next slide. Aniket, next slide. Now, we will be now discussing about the bar element. Now, as you may be knowing that the bar element is a pin joint, can carry only axial force. It can be used in modeling the truss. Wherever we have a truss system, we can use it in modeling to die. It has a properties which is ENA, which is known as extensional rigidity. Extensile rigidity, which is if E multiplied by A is high, it is deformation will be very small. Okay, the stiffness of this bar can be written as AE over L, which is also equivalent to P over delta or P over U. Okay. Now, if the bar is there is no fixed P on the node 1, then the displacement at the node 1 is U1, displacement at the node 2 is U2, similar to the spring you have seen. Then the stiffness can be written as AE over L 1 minus 1 minus 1 U1 by U2 P2 P1 by P2. This is the stiffness of the bar element. Okay, so I can write the element stiffness matrix. It's a nodal displacement multiplied by vector of nodal forces. If I take another same element and apply a transverse loading now, instead of applying the horizontal loading, now we are applying the perpendicular loading, vertical loading, which is shown on the right hand side. This is nothing but the bending of beam. The bending of beam, it can carry shear force and bending moment, and it can be used in modeling the frame. Frame can be a plane frame and it can be a space frame. And if I fix at the node 1 and apply the load at the node 2, vertical load at the node 2, then I can write down the very simple relationship PEI divided by LQ multiplied by V equal to P. The P is the load which is applied at the node 2, deflection at the node 2 is written as P, and 3E LQ is nothing but the stiffness. So stiffness into the load equal to the P. So this can also be said as equivalent to a vertical spring. Okay. Next, Aniket, next time. Now, beam element. There are two kinds of beam elements which are normally being used in the finite element. One is based on the Euler-Bernoulli beam theory. The other is based on the Timoshenko beam theory. Now, Euler-Bernoulli beam theory is does not account the deformation due to shear, due to transverse shear, and this is used in modeling the thin beam. Thin beam means length of the beam divided by the thickness, which is nothing but depth of the beam, should be greater than 10 or 20. Similarly, in Timoshenko beam, this can be used in modeling the shear deformation also, and this is used for modeling the thick beam. If we have a thick beam, that is the length divided by the thickness should be less than 10. Okay. The stiffness of a long beam, stiffness matrix of a long beam can be written as EI over L cube. This is what I have shown here, the stiffness matrix 4 by 4. Multiply the nodal displacement, which is one is the transverse deflection, other is the rotation at the node 1. Similarly, transverse deflection and rotation at the node 2. Load, which is nothing but the P1 and the moment M1. Next. Aniket, next, we can go. Okay. This can also be written as in a simple form. The element stimulus matrix, which is K, in multiply by V, which is nothing but the nodal displacement vector, equal to the load vector. Okay. If we have a short beam, instead of long beam, if I have a short beam, then the same stiffness can be written as, which I have shown in the next equation. That is EI L cube 1 plus phi. Phi is a non-dimensional number. And the same matrix 4 by 4 multiply by the nodal displacement and rotation at node 1, nodal displacement and rotation at the node 2, equal to the load vector, which is nothing but P1 M1 and P2 M2, where phi can be written as the 12 EI, which is nothing but the bending rigidity, flexural rigidity, divided by Ks into A G into L square. And if I substitute the value of G and I in this expression, this will convert into for mu equal to 0.3, 3.12 equal into the bracket D square by L square. Now this D by L whole square is the factor which we were telling in the thin beam and thick beam. That is the length divided by the depth. Okay. Now Ks into A is a shear area, and Ks is a shear correction factor, which is nothing but for rectangular section, cross section, it is 5 by 6. So therefore, the stiffness matrix which the above we have written can be written as the bending stiffness matrix. For a short beam can be written as the bending KB, bending stiffness plus the shear stiffness. This is the total stiffness which we can write in short. Okay, next. Yes, Aniket. If I have a beam, if it is loaded as a point load, vertical load, or if it is loaded as a uniformly distributed load or a triangular distributed load, then in the stiffness is same, this nodal displacement is same, only the load vector is changing. For a case of UDL, the load vector, which is nothing but P1 equal to, can be written as WL. W is the load per unit length, WL divided by 2 at the node 1, and at the node 2, WL divided by 2, which is same as total load. W is the load per unit length, L is the length of the beam. The total load is WL, half I put it at node 1, half I put it at node 2. Similarly, I can convert it to moment. WL is square by 12 at the node 1 and WL is square by 4 at the node 2. Okay. So only the change which we make is the load vector. Stiffness is same. Okay, let's see if I have a beam and apply a torque, which is mostly common in case of shaft. Then the torsional stiffness is nothing but the torque divided by the angle of twist, that is phi. Now if this also can be written in the form of the matrix. Next, Aniket, I can write down the torsional stiffness matrix Gj divided by L, 1 minus 1 minus 1, 1, 5 and 5, 2 equal to T1, T2. If a shaft has two nodes, then at two places I can apply the torque. They have a angle of this 5 and 5, 2, and the stiffness matrix is this. Okay. Now we are going to solve a very simple problem, cantilever beam having one element. And I will be trying to find the deflection at the node 2. Node 1 is fixed. It has a length L, and the flexure of rigidity is E and I. So stiffness matrix I can write it. Since at the node 1 it is fixed, we have V1 and theta was 0. Therefore, the first rows and column, second rows and column I can delete because of the boundary condition. And I get a equation, next, Aniket, next. Aniket, next, so I can write down the 2 by 2 matrix after deleting one row, one column, second row, second column. I get a equation 2 by 2 and V2 theta 2 equal to minus P 0 because there is no moment, only load is active. So these two equations can be written in the algebraic equation 1 and 2, and if I solve second equation, I can get theta 2, which can be linked with the y V2. This is written y, but it is V2. And if I substitute in equation 1 theta, then the deflection can be written is minus PL cube over 3I. And similarly, I can substitute in the equation 3, I get a theta 2. So I can get a vertical deflection PL cube over 3I. I can get at the node 2 rotation, which is PL square over 3I by finite element. And by closed form solution, we also know from the strength of material, the deflection is PL cube over 3I. Theta is equal to PL square over 3I. Now one thing is, remember that even one element, in case of beam element, one element can give the exact answer. As far as the deflection is concerned in one element, if I substitute this V2 and theta 2 in a shape function, because a shape function in between the deflection and the rotation can be calculated using shape function. If I use the shape function, at any point I can calculate both the deflection as well as rotation. And at more number of points, deflection and rotation can be calculated once the nodal values are known. Using this, we can plot the deflection pattern, which will be exactly same. Many people in finite element, they believe the two element in the finite element does not give the right answer. This is not correct. It gives the correct answer. No, you can do yourself. Okay, go to the next, Aniket. Okay, now the same equation for thick beam. The same cantilever, but now it is a very short cantilever. If I solve the equation is corrected by 5, 1 plus 5 here, and 4 plus 5. If I solve y2, vertical deflection, I get PLQ over 3I plus PL divided by KA into G, which is nothing but the deflection of a long beam PLQ over 3I, and PL divided by KAG is a deflection due to shear. Okay, so both the deflection for a short beam we can get. If we have a long beam, then the second will be very small. I can solve an example here. Example 1, I'm using a beam, cantilever beam, for E equal to 30 into 10 to the power 6, I equal to 864 inch square, flexure rigidity is 25 into 92 into 10 to the power 9, and length is 100 inch, load is 1 pound. If I solve it, I will get that deflection equal to 0.1286 10 to the power minus 4. Okay, next. And if I calculate delta S, deflection due to shear for this beam, we get the deflection will be around 1926 10 to the power 6. I think this is minus 6. There is a mistake in this calculation. It is not plus 6. Now in this you will find the deflection of bending is higher than deflection due to shear. Okay, because L over P, L over the depth D, L over L is 100 and depth is 12, that is 8.33. Okay, so it is very close to the 10. Okay, case 2 if I take, and if I take L equal to 10 inch, then I get a deflection delta B equal to 0.1286 10 to the power minus 7 inch, and deflection due to shear is 0.144 10 to the power minus 7 inch. So here you will find deflection due to shear is greater than deflection due to bending, and the reason is that L over T is equal to 10 by 12, okay, which is less than 1, more than 1. Now now we are solving a problem which is strength of material. It is difficult, but using finite element it is very simple. For example, let us take the clamp beam and apply the load at the middle. So I am taking here the one element which has a stiffness same. I am assuming it is a long beam. So I am not correcting with 5 shear deformation. So if I take the element 1 is stiffness matrix, element 2 stiffness matrix is same, except the change is the length one. Here let be small l equal to capital L divided by 2. Now if I add these two stiffness and I substitute the boundary condition at the node 1, that is V1 and theta 1, and similarly at the node 3, V3 at theta 3. If I delete first row first column, second row second column, the fifth row fifth column, sixth row sixth column, I left with only 2 by 2 matrix, which is nothing but EI over L cube, 12 plus 12 here, because that is a common node at the 2. Similarly, minus 6 plus 6 on the stiffness matrix. If I add these two, I will get 8 EI L cube, 24 0, 08 L square, and V2 theta 2 equal to P 0. If I solve that, I will get exactly 192 EI L cube into V3 equal to P, which is nothing but the deflection state we will get for a clamp beam having concentrated load at the center. The closed form, it is matching the closed form solution. Okay. And we know that theta 2 will be 0, which is coming already. So if you solve using finite element problem, strength of material problem, even with clamp beam, the solution is very easy to solve it. Whereas if you try to solve using strength of material, it is difficult. Similarly, I can now calculate the reactions at both the node 1 and node 3, which I have not done, you can calculate. Now, if I take a beam, same beam, I have only changed the load, which is nothing but a UDL now. The clamp beam having two elements having a UDL load. If I do that in the same way, only load changes. So load changes WL over 2 is the load at the node into 0. If this is the, and if I solve this equation, I will get V2 deflection is equal to WL 4 over 2 into 192 into EI. Slope is 0, and the deflection is matching the same using distance from material. WL 4 divided by 394 by EI. It is exact. Okay, this also is very simple to solve using finite element. Okay, next. Aniket, next time. Now, if I this is frequently used as a portal frame. Which has a stiffness K and K1 the K and K, the same stiffness in two columns, and which is at the top having a rigid beam, and the fixed at the bottom it is fixed. Both are fixed. Okay, the rigid beam. If a load is applied on the left hand side, the rigid beam moves horizontally, and the slope at the both columns connected to the column will be zero. In this case, I can model only one element and calculate what is the stiffness of this beam. A beam which is fixed at the bottom, having rotation at the other free end and load applied at the free end. This is the condition, boundary condition. So stiffness matrix I can write it. Similarly, if I do it first row, first column, second row, second column, and fourth row, fourth column. So I left with only EI over L2 into 12 into Y2 equal to P. And Y2 can be written as PL2 over 12 EI. The stiffness of the one column can be written as 12 EI over L square. And since these two are in parallel, the equivalent stiffness is nothing but K1, K2, which is 24 EI over L2. Straight away we can derive the stiffness of the both columns when they are identical. Okay. Next. Okay, next. This is another simplification. Now in the previous case, instead of fixing at the bottom is hinged now. Bottom is hinged. So I have a condition at the bottom is the deflection is 0 and there is a rotation, and at the top there is a deflection but the slope is changed. Okay. If I do that, I get the theta 1 T2. Okay. Theta 1 below and above is theta 2 is 0. Theta 1 V2. And I get already, if I solve, I can get V2 and theta 1. So V2 deflection, vertical deflection is PL square over 3I. Stiffness is 3E over L2, and the K effective, both are connected in parallel. So therefore, the effective stiffness is 6EI over L2. So straight away I can write the equivalent stiffness of the total frame, which is hinged at the bottom. Okay, next. Now, I am having a beam, which is, now I am trying to solve it here, a condensation problem. Now, in a beam, we have a vertical deflection, we have a rotation at one node. And if I want to develop a dynamic equation, which we will be demonstrating in the next lecture, then how to perform a dynamic condensation. In the same way, static condensation is also performed. So first I will be demonstrating the dynamic condensation problem. So in this case, I am taking two beam elements, and the load is applied at the third node. Okay, in the second element. Then stiffness matrix I can write is F1 M1. This is which I have written here. Now this stiffness and mass matrix can be written as ML 0, 0, 0, and we get about rotation 0 mass, about the displacement ML over 2. Similarly, about the rotation it is 0. This can be simply converted here. This is the degree of freedom is 1 I am deleting only 4 by 4 at the node 2 and the node 3. 2 degree of freedom, V1 theta 1, V2 theta 2, and V3 theta 2. Now, if I write the dynamic equation, free vibration of dynamic equation. Okay, next. Aniket, next. and changing here V2 into V3 and the order theta to theta 3, that order, if I change it, I get a mass matrix of a assembled mass matrix which I have written ml divided by 2, U2 U3 double dot, which is nothing but the acceleration, and the theta 2 theta 3, which is again the rotational acceleration. Similarly, this is collected to the mass matrix and the stiffness matrix. Similarly, we change U2 V3 U3 theta to theta 3 and the load vector. So now we can substitute, we can assume it is the harmonic motion, and then the another equation, this equation I can write out 2 by 2 matrix. I can partition 2 by 2 matrix, and they can be written as MPT 0 0 0 U C double dot U theta double dot equal to K T T K C theta K theta T K theta theta U C over U B 0 0. From these I can write the two equations, which is nothing but the matrix equation. MT is nothing but 2 by 2 matrix. UT is nothing but 2 by 1 vector. KTT is 2 by 2 stiffness matrix. UT is nothing but 2 by 1 matrix. And KT theta is 2 by 2 matrix. U theta is 2 by 2 matrix. Equation 1. Next. Another equation I can get linear algebra, which is again in a 2 by 2 matrix and 2 by 1 vector. Equation 2. From equation 2, I can find out U theta. U theta by minus K theta t into UT in the bracket is K theta t inverse. That is the 2 by 2 inverse matrix. If I substitute U theta in equation 1, I'll get the final equation. Final equation is MPT UT double dot plus UT into KTT equal to 0. Okay, next. Okay, so I get the equation. Now for the above problem, KTT can be written as KTT minus KT theta t K theta t into K theta theta inverse. So KTT is, first is KTT, which is EIL cube 24 minus 12 minus 12 12 minus K transpose theta t, which is nothing but 0 6L minus 6L 6L. Similarly, the K theta theta inverse is this 1 over 7L square minus 1 by 14L square 1 minus 1 by 14L square 2 by 7L square, and K theta t transverse of the first one. If I multiply all these things, I will get KTT nothing but EI L cube 6 by 7, 16 minus 5 minus 5 2, and if I substitute L, which is the total length of the beam, is equal to L by 2, I get a stiffness matrix. I get a stiffness matrix which is nothing but 48 divided by 7 EI over L cube 16 comma 5 minus 5 minus 5 2. This is a condensed matrix. This has only U2 and U3. U2 and U3. Let's we will solve a problem and demonstrate to you that whatever we are telling is right. Okay. Next. Aniket, the same problem which I am solving here, I am applying the load at the node 3. Okay. So I get the stiffness matrix 2 by 2 vector U2 U3 because theta 2 theta 3 I have eliminated, and the load is applied at the node 3, which is nothing but the node 2 there is no load, node 3 there is a load P. If I solve this equation, there are two equations I can solve this equation. I will get basically U3 PLQ over 3I, which is same as cantilever beam having the length L, And similarly the closed form solution is same. Similarly the U2 deflection I can also get 5L 48 PL cube divided by 48 pi, which is nothing but the deflection at the midpoint of node. So therefore the condensed matrix give the same answer when we are solving without condensation. Next. Now, if I want to calculate theta now, theta 1, theta 2, so I have a matrix, I have a u vector u theta, which is nothing but theta 1, theta 2, equal to minus k theta t ut into k theta theta inverse. So I have written that is 1 over L 6 by 7, the inverse matrix into the 2 k theta t and ut. Only k theta t and ut, if I multiply, I'll get this equation. So this can be written as theta 2, and if theta 2, if I solve it, simplify it, I will PL square over 2 EI exact. So nothing but the exact. Rotation at the third point. So node number 3. Okay. So I can get the same. Either I can use condensed matrix, after doing the condensation, I should get the same answer. Okay. This is I am doing because I have a mass matrix related to theta rotation 0. So if I calculate the eigenvalue and eigenmode, I should have a matrix where diagonals are not. That is the reason why I am doing this. Okay. Next. Now, I am only explaining you here that if I have a simply supported beam and the load is acting at the center, then the deflection at the center is PLQ over 192 EI. If I have a thick beam, 4 plus 5, this is the Timchenko solution. This is when you assume the beam is a short beam and you are applying the load in a simply supported short beam at the center point, I'll get the deflection in which you would get 5 appears. If beam is long, then I will get only the first part, PL cube over 192 EI multiplied by 4, which is nothing but PL cube 48 EI, which is nothing but this formula is for long beam. Similarly, if I have a simply supported beam, UDL load, I get for a thick beam, the QL4 over 386 EI, 5 plus 5, a thick beam. If it is a long beam, then it can be written as 5L4, 384 EI for thin beam. Okay, and the cross section I have shown on 5 value also I have given. For B equal to 0.3. So for thick beam, we have a higher deflection at the center, whereas thin beam you have a slightly less. But again depending upon the L over D ratio. Okay. Next. Okay, beam can be solved. Beam problem can be solved using following element. 1D element which we have discussed just now. We can use the long beam formula developed by using either the Bernoulli theorem or Timchenko beam theorem. Now these are based on bending theory. The beam problem can also be solved by using theory of elasticity, where 2D element can be used, and another way the 3D element I can use. But if I am using 1D element, then it can be a thick and thin. 2D element, it can be a plane stress type element I can take, 4-noded or triangular element or quadrilateral element. And in case of 3D element, it can be penta, hexa, prism or pyramid. A number of options are available. Now, degree of freedom in the 1D element are the transverse deflection and rotation per node, whereas the degree of freedom in the plane stress element is U and V at per node, and as in the dimension is UVW. Okay. Now, for the beam problem, obviously we use the type of one element. Type 2 element when were used, if you have any opening, etc. In case of beam, if in the beam if you have some opening, then you can use two element, the second element, second, which is based on theory of elasticity, and third, the 3D element can be used if you will find that shear deformation, deflection due to shear deformation, which is included in 1D element, is a approximate one. If you want to do a very detailed analysis, even for a short beam, 3D element is preferred. Okay, so 3D element has always choice in the final, but the degree of freedom, if you move from 1D element to 2D element to 3D element, they will go on increasing. Next. Okay, Aniket. Now, 2D element, uh, four noded element, if I want to solve a beam element, a beam problem using four noded element, 2D, we can use 8 noded hexahedron element in 3. They are all linear elements. They suffer a severe drawbacks about that they cannot be bent like the bending of beam in 1D. Their bending behavior is very, very poor. To improve the bending behavior, we add a additional shape function at the center, node 5th, and the degree of freedom which is added is 1 minus s square a1, 1 minus t square a2 is u. Similarly in V, 1 minus a square a3, 1 minus t square a4. This 1 minus s square and 1 minus t square, they are the bubble mode. Now, if you find, if by adding the node 5, you will find that it has a 12 by 12 degree of freedom. If you are not adding the node 5th, then it has a 8 by 8 size of the element. Okay, stiffness element, stiffness matrix. Now, this adding a node 5 has added 4 degree of freedom, which is nothing but A1, A2, A3, A4. This I have to condense. So I can write down the equation, which is nothing but KDD, 8 by 8, and KDA, KAD, KAA, which is 4 by 4, D into A vector, and the load at the node at the centroid. So if I solve this matrix, okay. Next, if I solve this matrix, Aniket, next. If I solve this matrix, I can get A equal to this, and KDT. I substitute in the next, I can get KDD into D into FD, which is nothing but the condensed matrix. And this will have a much better bending behavior, much better behavior, both in case of 2D element and 3D element. But they are incompatible elements. So therefore, in almost all code, when we are using the 4-noded element in 2D, 8-noded element in 3D, we always use incompatible element where one node at the center is added, which is known as bubble node, and which is finally condensed and has a better stiffness, bending stiffness property. And this is available in almost all. Okay. Next, Aniket. Aniket, next.
Done, sir. This is the last slide.
Okay. Well, thank you very much. When we are now going to solve one problem. Okay, Aniket, we can start solving the clamp plate.
Yes.
Any
Question?
question is there that we can ask.
Please, they can ask.
If any question is there, they can ask. Next, we are going to solve a square clamped plate, which is nothing but the extension of a 2D beam. We have discussed 1D beam. We can say it is equivalent to 2D beam. It has a 2 dimension, X and Y. Normally, beam is there in X direction, and it is lying in a plane, the YX plane, and the Z is perpendicular to that. But the plate will be in XY plane, and Z will be in thickness direction. Okay. So, Aniket, you start. This is the plate.
Yes, sir. Yes.
Following dimension given in the. Okay. You can.
So now in this we are going to solve a problem of a clamped plate, circular plate, or sorry, square plate,
Rectangle. Square.
rectangular plate having uniform loading onto it. Okay, so the reference is taken from Timoshenko book, Theory of Potential. And the analysis type which we are going to solve is static analysis, and the type of element which we are going to use is 2D element. So our intention is to determine the deformation and stresses in the clamp plate with uniform pressure of 10 MPa. So these are the material properties. So E value is 200 GPa. Poisson's ratio 0.3. Geometric properties are in mm.
Hello, sir. Just a second. Can I interrupt? You uniform pressure, right? You said uniform pressure on the platform.
Can you ask the question again, sir?
You said uniform load on the square clamp. Is it?
Yes.
Square plate UDL load. Pressure is like UDL.
UDL. Acha. So over the total area, na? Acha. Okay.
Yes.
Okay. So now the geometric properties are in mm, and the value of pressure which we are going to apply is 10 MPa. That is Newton per mm square. So now in this case, we have to be consistent with the unit system. So the Young's modulus is 200 GPa. That means we have to apply this value of Young's modulus Newton per mm square, that is MPa. So that is 200 into 10 to the power 3 MPa is the value of Young's modulus. Poisson's ratio is 0.3, and the geometric properties are in mm. So we will see how we can model this in P. So I'll just open the software. In colors, I'll just switch on to white color so that it's visible as in the last problem we have solved. Okay. So I'll go to the main tab from where we have used the commands. In geometry, I'll create a point. In geometry, I'll create a point at the origin with an entity ID as point 1. So here you can see the plate is square plate. So the dimensions are 1000 by 1000. So first point I'll create at the origin, and the second point I'll create at 1000 in X and 1000 in Y. That is another point I'll create at diagonal. So this will be a second point. Diagonal point I'll generate. I'll go to settings and sizes, and I'll just increase the size of the point so that it will be visible onto the screen. Now it is properly visible. So 2 points we have created. First point at the origin, that is 0, 0, 0. Second point we have created at x thousand and y thousand. Z is 0.
So 2 points we
2
have
points we
created.
have created.
I'll go back
I'll go back to the main menu.
Once these
Once these
points are
created,
created,
we have to
join these two
join these
points
2
to
points
generate
to
a
generate a
surface.
surface.
So in order to
create a
surface,
surface,
we can go to surface
option,
create,
create, and rectangle 2 point.
we have this
rectangle 2 point
so
option.
that
So that
we can simply select first point which is origin point and another point which is diagonal point. So rectangle 2 point can be used to generate a surface. I'll double click to invoke the command. As we have solved one problem in the previous session, you are familiar with this filter. I'll choose point filter. I'll select first point and second point. So a surface is created. I'll just use this fill command and just hovering my mouse onto the command so that it will give a proper color to the surface. Now
our geometry is
done.
done. Our geometry is ready.
As we have to follow the sequence. First we will create the geometry. Then we will mesh it. Then we will apply loads and boundary condition, and we will assign the physical and material property. Geometry is done. We will move on to the meshing section. In mesh, we will use FE mesh. In the first session, in the second session, we have solved a cantilever beam problem. So we have used this command called bar. Now since we are solving a 2D problem,
we are solving
we
a
are
2D
using
problem.
this
We are using
quad triad.
And triad.
So these are the 2D elements.
So these are the 2D
element and triangular
quadrilateral element and triangular.
What preference we will give?
What preference we will give to this quad element?
Double click on this
quad element to invoke the command.
In the surface, I'll choose the surface. And here we have the method. So software has two options. Either you can do map meshing, or else you can do auto meshing. So I choose map meshing. Since the geometry is simple, I'll use map meshing. Type here we have 4-noded element and 8-noded element. So 4-noded element means we have a linear element, and we have the second order. So we will stick on to 4-noded element for now. There are two options given to the user. First option is the initial size, where the user can directly give initial size for meshing. Or else another option is division option, where the elements can be controlled by the user based on the divisions. So I will click on division, and I'll adjust the divisions as per our requirement. I use left to increase the mesh density. See on the adjacent side, on the opposite side, I'm using my left mouse button to increase the mesh density. You can simply click on this edge, and you can use left to increase the mesh density, and right click to decrease the mesh density. And you can click on apply. So the meshing is done. It will create quad elements. I'll just change the color of the elements so that it will be visible to all. And I'll just hide the nodes. Now I think it is properly visible to all. Okay. So I'll return back to the main tab.
So
in
in
geometry
geometry,
we
we
have
have
created
created 2 points,
2 points
and
and
we
we
have
have
used
used
rectangle
rectangle 2-point
2-point
option
option
in
in
the
the surface
surface
to
to
generate
generate
a
a
surface.
surface. Then we have
Then
mesh
we have
using
mesh
quad
using quad
elements.
elements.
Now
Now
I'll go to
I'll go to the
PDF.
PDF.
So here
So here
you can
you
see
can see
we have
we
to
have to
arrest
arrest
we have to
we have to
arrest
arrest
all the degrees
all
of
the
our
degrees of our
freedom
freedom
at the
at the
edges
edges
since it is
since it is
clamped.
clamped.
So
So I'll go to loads.
I'll go to
I'll go to loads,
structure.
structural.
I'll go to
I'll go to loads,
structural
structural,
displacement.
displacement.
I'll go to
I'll go to loads,
structure
structural,
displacement
displacement,
and add.
and add.
So
So here we have to
apply
apply
the boundary
the boundary
conditions.
conditions.
So node
So node IDs,
here
here we have to choose the node IDs
which are
which are
present at
present
the
at the
edges.
edges.
So for that
So for that we have some
filters
filters
available
available
at the top.
at the top.
So
Here first filter is
if it is
if it
curve,
is curve,
you can select
you
the
can select
curve.
the curve.
If it is
If it is
surface, you can
surface,
select
you
the
can select the
surface.
surface.
If it is
If it is
volume, you can
volume,
select the
you can select
volume.
the volume.
Similarly,
Similarly, here we have surface edge,
volume
volume
edge,
edge,
like this.
like this.
So I'll
I'll
choose
choose
surface
surface
edge
edge
so that
so that
by
by
single click,
single click
all
all
the
the
nodes at
nodes
the
at
edges will
the
be
edges will be
selected.
selected.
I'll
I'll
also
also
choose
choose
or
or
I'll
I'll
click
click
on
on
this
this
edge.
edge.
So all the
So all
nodes
the
present
nodes
at the
present
edges
at
will be
the edges will be
selected.
selected.
Similarly on this
Similarly, on
side
this
as well
side
as on
as
this
well as
side,
on
I'll
this side, I
choose.
will choose.
And in the
And
boundary
in the
condition
boundary condition
values,
values,
that is
that
in
is
BC
in BC
values,
values,
I'll
I'll
arrest
arrest
all degrees
all
of
degrees
freedom.
of freedom.
I'll simply
I'll simply
all degrees
arrest
of
all degrees
freedom.
of freedom.
So now
So
it
now
will
it
behave,
will behave,
it is clamped.
it is clamped. Now you can see we
apply the
have
boundary
applied the boundary
conditions.
conditions.
I'll just
I'll
repeat the
just repeat the
process again
process
so that
again so
it will
that
be
it
clear
will
to
be
all.
clear to all.
I'll press
I'll
Ctrl
press
Z.
Ctrl Z.
In the main
In the main
we
tab,
will go to
we will go to
loads,
loads,
structural
structural
displacement,
displacement,
add.
add.
In node
In node IDs, we have to choose nodes which are
present at the
present at the
edges.
edges.
In order to
In order to
select the
select
nodes
the
which are
nodes which
only
are
on the
only on the
edges,
edges,
you can
you can
use the
use the
filters which are
filters
present
which are
at the
present
top.
at the top.
In this,
In
I'll
this,
use
I'll
this
use this
fourth
fourth
filter,
filter,
which is called
which is
as
called as
surface edge.
surface edge.
I'll choose
I'll choose
node,
nodes at
this
this
edge,
edge, left side edge.
adjacent edge
Adjacent
also I'll
edge also I'll
select.
select.
So with
So
a
with
single
a
click,
single
all
click,
the
all
edges
the
you
edges
can
you
select.
can select.
In the boundary
In the
condition
boundary condition values,
I'll
I'll
simply
simply
arrest all
erase
degrees
all
of
degrees of
freedom
freedom
and apply.
and apply. I'll use control and left mouse button to rotate the model.
Control the right
Control
click
the
to
right
pan
click
the
to pan
model,
the model.
and control
And control scroll
zoom in,
for
zoom
zoom
out.
in, zoom out.
Control
Control
scroll for
scroll
zoom in,
for
zoom
zoom
out.
in, zoom out. Now,
The boundary
the
condition
boundary
is
condition
added.
is
Our
added.
next
Our
step
next step
is to
is to
apply the
apply
value
the
of
value
pressure.
of pressure.
So in order
So
to
in order to
apply the
apply the
pressure,
pressure,
you can
you can go to loads,
structural.
structural.
Here we have
Here
this
we have this
pressure. In the
pressure.
previous
In the
problem
previous
of a
problem of
cantilever
a
beam, we
cantilever
have
beam, we have
applied
applied
point load.
point load.
In this
In
case,
this case,
we are going
we are
to
going to
apply
apply
pressure
pressure
on the
on the
entire
entire
faces.
face.
So I'll go
So
to
I'll go to
pressure,
pressure,
add.
add. Here I have to select the element faces. So if you click on this face, it will select one by one. In order to select the entire face on a single face, you can use this isoface option. I'll use this eye option, eye filter. I'm just hovering my mouse so that it will be visible. So here we have this eye filter, that is isoface. So on
you can select the entire faces,
and the value
10
of 10
MPa we have to
MPa we have
apply.
to apply.
So I'll
So I'll
choose
choose
the value
the
of
value of
pressure
pressure
as 10.
as 10.
Direction
Direction
you can
you
keep
can keep
normal,
normal,
or else you
or
can
else you
give the
can give the
direction.
direction.
I'll give
I'll
Z.
give Z.
If I'm
If I'm
applying the
applying
value
the
of
value of
10 MPa
10
in
MPa
Z,
in Z,
so I have to
so I
give
have to give
negative
negative
value,
value
negative,
negative,
so that
so
it
that
will
it
act
will
in the
act in the
downward
downward
direction. So that
direction.
load
So
is
that
going
load
to
is
act,
going
or
to
the
act,
pressure
or
is
the
going to
pressure is
act
going
in the
to act in the
downward
downward
direction
direction
of Z.
of Z.
Coordinates,
Coordinate system,
it is
it is
Cartesian. 0
Cartesian.
means
0
Cartesian
means
coordinate
Cartesian
system.
coordinate system.
Set
Set
ID, we will
ID,
keep it
we will
as
keep it as
1
1
default.
default.
Label, you
Label,
can
you
label it
can
as,
label it
you
as
can rename it as, you can rename it as pressure. You can rename it as,
you can rename it as
you can rename it as pressure.
you can rename it as pressure
10 MPa.
10 MPa.
And you can click on,
And you can click on apply.
in the message box you can see
In the message box
the
you can
pressure is
see
added.
the pressure is added.
So we have
So we have
created the
created
geometry,
the
we
geometry,
have meshed
we
it
have meshed it
using quad
using
elements,
quad
we
elements,
have
we have
applied the
applied
boundary
the boundary
condition to the
condition to
edges,
the edges,
and then we have
and then
applied
we
the
have
pressure
applied the
value
pressure
of 10
value of 10
MPa
MPa
on the
on
element
the element
faces. Now
faces. Now
we will move
we
on
will
to the
move on to the
property section.
property section.
In the
In the
properties we have to
properties we have
assign
to
the
assign
material
the material
property.
property.
In the
In the
material
material
we have
we have Young's
modulus
modulus
as 200
as
GPa,
200
that is it
GPa,
is
that is it is
steel
steel
with Poisson's
with
ratio as
Poisson's ratio as
0.3.
0.3.
I'll go to
I'll go to structural
isotope.
isotropic.
Here
Here
type
I'll
element
type
as all.
element as
You can
all. You
simply
can
type
simply type
elements
elements
as all.
as
Since
all.
it is
Since it is
uniform, the
uniform,
material is
the material
same
is same
throughout.
throughout.
So you can
So
type
you can
element
type
IDs as
element
all.
IDs as all.
Material,
Material
I'll
data,
click on
I'll
dialog
click on
box,
dialog box.
and here I
And
have to
here
fill
I
the
have to fill the
information.
information.
In the previous
In the
session, we
previous
have
session, we have
seen
seen
on the Young's
on the Young's
modulus we have
modulus we have
given
given
for
for
the
the
cantilever
cantilever
problem or 1D
problem or
problems.
1D problems.
Now, since we are
Now, since
working
we are
with
working with
2D,
2D,
we have
we
to
have
give
to
the
give the
Poisson's ratio
Poisson's ratio
also.
also.
So the
So the
modulus
Young's
is
modulus is
200
200
GPa, that means
GPa, that means
200 E3.
200 E3.
Now it
Now it will become
per
Newton
mm
per
square.
mm square.
Poisson's ratio
Poisson's
is
ratio
zero
as
point 0.3.
0.3.
If you want
If you want to add this material to the library, here we have option to add the material to the library.
I'll add it
I'll
as
add it as still
one
1
and apply.
and apply.
I'll
I'll click on apply.
so the
So the
material
material
is
is added.
here.
Here we have another options like material name. If you want to give the name of material to recognize in further analysis,
So you can
so
give
you
the
can
name
give the
as
name as
steel,
steel,
or as per
or
your
as per your
convenience,
convenience, you can
the
define the name to the
material.
material.
So here,
So here the material is added.
after
After assigning the material properties, our next step
is to
is to
assign
assign
the
the
physical
physical
property.
property.
In the physical
In the physical
I'll
properties,
go to
I'll go to
thickness.
thickness.
Since
Since it is a
2D
2D
problem, we have to
problem, we have
assign
to
the
assign a
thickness.
thickness.
For 1D,
For
we have to
1D, we have
assign
to
a cross
assign a
section.
cross section.
For 2D,
For 2D, we are going to
assign a
assign a
thickness. So
thickness.
I'll double
So I'll
click on
double
this.
click on this. and I'll add.
Element,
Element
the
again,
thickness
the
is
thickness is
uniform.
uniform.
The plate has
Plate
uniform
has uniform
thickness.
thickness.
So
So
I'll give
I'll
element
give
IDs
element
as
IDs
all.
as all.
So to all
So to
the
all the
elements, we will
elements, we will
assign thickness
assign thickness
value.
value.
We'll just check the
We'll just
value of
check the value of
thickness.
thickness.
Thickness
Thickness value is
50
50
mm.
mm.
So I'll give
So I'll give the value of
as
thickness
50.
as 50.
If you want to
If you want to give label, I'll
label
give
as
label as
thickness
thickness
50 mm.
50 mm.
Apply.
Apply.
At
At any moment, if you want to change any
you can
data, you
simply
can
go to
simply
this
go to
edit
this
tab,
edit tab,
and you can
and you
check
can
here. You
check
can
here.
see
You can
here it
see here it
is
is
material
material
pressure of 10
pressure of 10
MPa.
MPa.
The label
The
which
label
we
which
have
we have
given as
given
pressure
as
10
pressure 10
MPa,
MPa,
thickness 50
thickness
mm.
50 mm.
So I'll go back.
So I'll go back to main tab.
Now we
Now
will just
we will
quickly
just
check.
quickly check.
We have
We
created
have
the
created the
geometry.
geometry. We have
We
meshed it.
have
We
applied the
have
boundary
applied the boundary
condition to the
condition to
edges.
the edges.
Then we have
Then
applied
we
the
have applied the
pressure.
pressure.
Then in
Then in
properties we have
properties, we
assigned
have
the
assigned
material
the material
property,
property,
and finally
and
the
finally
physical
the
property.
physical property.
So
So
almost
almost all the inputs
are
are
assigned
assigned
to the
to
model.
the model.
Now we will
Now we will move on.
now we will
Now
move
we will
on
move
to
on to
analysis.
analysis.
In the
In the analysis type, in the
analysis type,
analysis type,
we will
we
choose
will choose
static.
static.
In the analysis,
In the analysis
we
type,
will click
we
on
will click
static,
on static,
and we
and we will
double
simply
click
double
on the
click
run
on the
solver,
run
because
solver, because
all
almost
the
all
input
the input
data
data
is given.
is given.
Our final
Our
step is
final
to
step
solve.
is to solve.
So I'll
So
double
I'll
click on
double
the run
click on the
solver
run solver
to solve the
to
model.
solve the model.
Before solving,
Before
it will
solving,
ask
it
me
will
to
ask
save the
me to
file,
save the
because we
file
know
because
where
we
we
know
have
where
saved
we
the
have
model.
saved the model.
So I'll
So I'll
simply name
simply
it
name
as
it as
clamped plate,
clamped plate,
and
and the
file
file
name will
name
be
will be
clampedplate.vrj.
clampedplate.vrj.
Extension will be
Extension will be
.vrj.
.vrj.
I'll click on
I'll click
save.
on save.
Once you click,
Once you click on save,
it will
it
show
will
that the
show that
solver
the
is feasibility. It will show the software is
software is the solver is
analysis type is
SMT,
static,
analysis type is static,
and the input file is
and the
present at
input
this
file is
location with
present
the
at
data
this location
as
with
a
the data
.dat, and
as
the
a
output file
.dat,
will be
and the
present at the
output
same
file will be
location
present
with the
at the same
extension as
location with the
.com.
extension as
I'll
.com.
click on yes, and
I'll
it will
click on
start
yes,
solving
and
the
it will
problem.
start solving the problem.
So here you can see
So here you can see it
solved the
has
problem.
solved the problem.
If there is any error,
If there is
it will
any
give in
error,
the
it will
message
give in
box.
the message box.
If there is
If there's any error
end,
at
you
your
can
end,
just
you can
please
just please
ask
ask
the error, or
the
you tell
error,
the
or you
error.
tell
We
the
will
error.
sort
We
out
will
the
sort
issue.
out the issue.
If there is
If
any
there is
error
any
while
error
creating the
while
model,
creating
you
the
can
model,
please
you can please
unmute your mic
unmute
and you can
your
please
mic, and you
ask.
can please ask.
Till then, we will move.
Till then, we will move forward.
Now analysis is
Now
complete.
analysis
Our
is
next
complete.
step
Our next step
is to go to post,
is to go to post,
and
and
we check the deform
we
shape.
will check the
In
deform
the
shape.
deform shape, you
In
can
the deform
animate the
shape, you can
deflection.
animate the
I'll just
deflection.
rotate.
I'll just rotate.
I'll just
I'll
animate the
just
deflection.
animate the deflection.
And here you can see
And here
we
you can
have
see we have
deform shape without
deform shapes
contours.
without contours.
If you want to see the
If you
results
want to
with the
see the
color
results
contours,
with
you
the
can go
color
to
contours,
post
you can go
contours,
to post
and you
contour,
can animate the
and you can
deflection.
animate the deflection.
You can animate the
You can animate the deflection.
So here
So here
I'll just simply
I'll
animate
just
the
simply animate the
deflection.
deflection. So displacement, here the component is TRES. TRES means translation resultant. That is resultant values it is showing. The type here is band. If you want a smooth graph or smooth plot,
you
you
can
can
smooth.
type smooth.
You will get this.
You will get the smooth color contour.
If you want to
If you want to plot the value of
stress,
stress, you can click on stress
and you can
and
click
you
on
can click
apply.
on apply. You will
these
get these
stresses.
stresses.
Excuse me.
Yes.
Yes.
My screen is showing vectors of this pressure on the surface. How to remove that?
So
Below help, I'm
I'm
just
just
hovering
hovering
my
my mouse.
mouse.
Can you show?
Can you show?
Can
Can
you
you
see
see
the
the
command?
command?
I'm just
I'm
hovering
just
my
hovering my
mouse
mouse
onto
to
the
the
command.
command.
Yes, I can see. Yeah.
Can you see?
Can you see?
Yeah,
Yeah,
yeah.
yeah.
Yeah,
You
yeah.
click on
You
that.
click on that.
It will
It
hide
will hide
the
the
values.
values
Okay.
Or the
or the
representation it will
representation.
hide.
It will hide.
Okay. Also, like, where is the command to animate? Can you please show that once more?
If you want
If
to
you want to
animate, you
animate,
can
you
go to
can go to
post
post
contour,
contour,
and
and
here
here you click on deform.
on deform.
On deform.
You first click
First
on
click on
deform,
deform,
then
then it will
the
highlight the
animated
animate
section, then you
deflection,
click
then
on
you click on
animated section.
animatic section.
So here
So
we have
here we
this,
have this,
we will
we
simply
just
scroll
simply
down.
scroll down.
Okay. Okay. Got it. Thank you. Thank you.
Yes.
Yeah.
If
If you want to plot
the
the
results
results
in the
in
form
the form of
graphs,
graphs,
then you
then you
can
can
go to
go to
post,
post,
path plot.
path plot.
Here we have
Here we
this
have this
post,
post,
path plot
path plot
option.
option.
Simply
Simply
double click
double
on
click
path
on path
plot
plot
and
and select the
nodal
nodal
path.
path.
For
For
now, I'll
now, I'll
select
select
the nodal
the nodal
path
path
as my
as my
vertical
vertical
line.
line.
So
So here you can see
vertical
vertical line I'm
choosing,
choosing,
and I'll click.
and I'll click on apply.
So
So it will
a
give me
graph
a graph
of
of
displacement
displacement
with
with
respect to
respect to
distance.
distance.
So here you
So
can
here you
see
can see
the
the
length
length
of
of
the
the
plate
plate
or the
or
dimensions
dimensions
of
of
the
the
plate
plate
is
is
1000.
1000.
So
So the distance is 1000,
and this is
and
the
this is the
maximum
maximum
value of
value of
displacement
we are
getting
getting
at the
at
center.
the center.
That is
That
at
is at
distance of
distance of
500
500
mm.
mm.
अच्छा, मैं अभी एक वेबिनार में हूँ। हाँ, वेबिनार में हूँ। हाँ, वेबिनार में हूँ मैं अभी। हाँ, हाँ, ठीक है।
If you
If you want to
export the
export the
results
results
to
to like
Excel,
Excel,
you
you
can
can
go
go
to
to
view
view
results
results
in post. In post,
in post. You can go to view
results,
results,
displacement.
displacement.
If
So
I
if
want
I
to
want
see the
to see the
results
results
of
of
this
this
vertical
vertical
nodal
nodal
path,
path,
I can
I
choose
can
that
choose
nodal
that nodal
path,
path,
and this
and
will
this
be
will be
my
my
these
these
are
are my
displacement
displacement
values
values
in Z.
in Z.
So
So I can simply copy this. I
I
can
can copy
copy
all
all
this
this
information.
information.
I'll choose
I'll choose
Control
Control
A.
A.
I'll
I'll
copy,
copy,
and I
and I
can paste
can
it
paste it
into
into
Excel.
Excel.
Simply
You can simply
into
paste it
Excel.
into Excel.
So even that
So even that
functionality is
functionality is
available.
available. If you want to plot the reaction forces, you
go to
can go to
displacement and
displacement
click on
and click on
reaction, so you will
reaction.
get
So
the
you will get
reaction
the reaction
forces.
forces.
Since now I have selected only the vertical
Since now
line,
I have
at
selected
the
only the vertical
top
line,
and
so
bottom
at
are
the
fixed only 10
top
and
and bottom are fixed
352 word
only 10
number.
and 352 node number.
we
At
are getting the
this two
results.
node numbers, we
So
are getting the
here
result.
I'll
So
choose
here
node
I'll
as
choose
all.
node as
So
all.
it will give
So it
me
will give
the
me
reaction
the reaction
forces
forces
only where the
only
boundary
where the
condition is
boundary
applied.
condition is applied.
So these are the
So these are
reaction
the reaction
forces
forces
which we have.
which we have applied. You can also go to
location
the
where
location where
the
the
problem is
problem
saved.
is
I'll just
saved.
go to the
I'll just go to
location
the location
where the problem is
where the
saved.
problem is saved.
Clamp.
Clamped plate.
Um, I'll use
I'll
this
use
data
this
file,
data file,
that file.
that
I'll
file.
double
I'll
click
double
to open
click
the
to
data
open the
file.
data file.
So here you
So
can
here
see
you
this
can
is
see this
the
is the
input file
input file
which
which
will
will
be
be
available
available
at
at
your
your
location where you have
location where
saved the
you have
model.
saved the model.
So all the
So all
nodal
the nodal
information,
information,
element
element
information,
information,
as well as
as
load and
well as
boundary
load and boundary
condition
condition
values are
values are
available.
available.
So
So at
at
any
any moment,
moment,
if
if
you
you
want
want
to
to
change
change
the
the
data,
data,
you
you
can
can
simply
simply change
change it
it
here
here as
also, and you can save
also, and you
this,
can save this,
and
and
directly open
you can
this file
directly
in
open this
paste.
file in paste.
So this is a
So this is
notepad
basically a
file.
notepad
If I
file.
want to
If I
change the
want to
value of
change the
pressure,
value of
I
pressure,
can simply change the
I can
value of
simply change the
pressure
value
here
of pressure
itself,
here itself,
and I can save
and
this
I can
file,
save this file,
which is a notepad
which is a
file,
notepad file,
and I
and
can open
I can
feast and I
open
can
feast
directly
and I can
fire a
directly
job.
fire a job.
So
So
this
this
value
value
editing is
editing
possible
is
in notepad
possible in
also,
Notepad also,
and the output
and the output can be
in the
seen
notepad
in the
itself.
Notepad
I'll just
itself.
double
I'll
click
just
and
double
open
click
the
and
output
open the
file.
output file.
So these are the
So these are the
displacement
displacement
results
results
in the output
in the output format.
then
Then these are
reaction
the reaction
forces.
forces.
So all the
So all the
the output
data
is
or the
available
output is
in this
available
output
in this
file.
output file.
So if there's
So
any
if there is any
question,
question,
you can please
you can
ask.
please ask.
For any data analysis in software field?
Data
Data
analysis means
analysis means
can you
can you
elaborate
elaborate
the question, ma'am?
the
Because
question, ma'am? Because
Yeah, any if you have any
hello.
data. Hello, suppose if you have any data in Excel sheet.
yes,
So,
yes,
Yes, yes.
yeah.
Yeah, if you have any
Data in the
data in
Excel
the
sheet,
Excel
and
sheet,
if you
and
want to
if you
import
want to
in paste,
import in
even that
paste,
is
even that is
possible.
possible.
So
For
example,
example,
I'll just give
I'll
an
just give an
example. Like
example.
if you
If you
have
have
the,
the,
I'll just go
I'll
to
just go to
material
material
properties.
properties.
I'll go to
I'll go to
material
material
properties. If I
properties. If I
have
have
data in the
data in
Excel
the
sheet,
Excel sheet,
I
I can
can
simply
simply import
import
that in
that
the
in the
table.
table.
So
So
from this
from this
table
table
option,
option,
we
we
can
can
either
either
import
import the
a file
a
from
file
the
from the
Excel.
Excel.
So from
So
Excel
from
we can
Excel we
import.
can
That's
import.
not an
That's not
issue.
an issue.
Sir, I just wanted to ask one doubt. Uh, I might have missed it, but hello, can you hear me?
Yeah,
Yeah,
listening. Yes, sir.
listening.
Yes,
Yes,
sir.
sir. Yes,
Please
sir.
tell me.
Please tell me.
Okay, so regarding the material properties, no, are they specified as per ASME section 2, part A, part D, or are the materials specified as generic materials like mild steel or cast steel or?
Yes,
Yes,
yes.
yes.
Currently, it is
Currently, it is
generic
a generic
material,
material,
but
but
as
as
per
per
the
the
requirement,
requirement,
currently
currently
VSSC
VSSC
is
is
working
working
on
on
that.
that.
For
For
Section
ASME
8
Section
Division
8
1,
Division
2,
1,
as per
2,
their
as per their
requirements,
requirements,
they are
they are
creating the
creating the
library
library
where the
where the
user can
user can
download the
download the
complete
complete
material
material
library,
library,
so that
so that
according to
according
the
to the
sections
sections
they
they
can
can
use that
use that
material.
material.
And the similar type of calculation and analysis also can be done in PBA light, no?
Yes, sir.
Yes, sir. Yes.
For pressure vessels.
Hello?
Hello, hello. Yeah, is it audible?
Hello. Yeah, is it audible?
Hello.
Yeah,
Is it
you got
audible?
cut
Hello? Yes,
now.
sir. Yes, sir.
Yeah,
For
it's now.
PV
Yes,
light,
sir.
Yeah.
Yes, sir.
yes,
For
PV light is
PV
there.
light, PV light is there.
So the PV light is
The PV light
basically
is
completely dedicated to pressure
basically
vessel
completely
design.
dedicated to pressure vessel design.
And this is a general
Hmm.
purpose
And this is
software
a
which
general
can be
purpose
used for
software
all. But
can be
it
used
has
for all.
a
But it
capability
has
to solve
a
a
capability
problem
to
of pressure
solve a
vessels.
problem of
So in
pressure vessels.
basically
So
BARC, that
in
is Baba
basically
Atomic Research
BARC,
Center,
that is Baba
this
Atomic
piece
Research
is
Center,
quite
this
widely
piece is
used for
quite
design and
widely used
analysis
for
of pressure
design and
vessels.
analysis of pressure vessels.
Acha. Okay. ठीक है. Thank you. Thank you.
Yeah, okay.
Okay.
Excuse me, just one question more.
Yes, sir, please.
Hello.
Yes, sir. Please.
Yes, sir, yes, sir,
So
please.
this,
Ask.
I think,
Yes, sir. Yes, sir. Please.
can this software be used for generating mesh or loading a mesh file into this, like maybe for CFD
Yes, it is
applications?
possible.
Yes,
Yes, yes, yes, yes. It is
yes,
possible.
yes, yes, yes.
So
It
Yeah,
is possible.
yeah.
So
it has N-PAR
it has
capabilities like
NPAR
hypermesh for
capabilities like
meshing.
hypermesh for
So this piece
meshing.
has
So
excellent
this
meshing
piece has excellent
capabilities.
meshing capabilities.
Various different capabilities. We have
Different
already
capabilities.
uploaded
We
some
have
of
already
the
uploaded some of the
capabilities on YouTube.
capabilities on
So even you
YouTube.
can watch
So
some of the
even you
videos
can
on
watch some
YouTube
of the
where
videos on YouTube where
meshing techniques and
meshing
meshing
techniques
capabilities
and
are
meshing
shown.
capabilities are shown.
And complex models can
Complex
be
models can
meshed in
be
fees.
meshed in fees.
It may be 2D,
It
it
may
may
be
be
2D, it
3D.
may be
It
3D.
can be
It
exported
can be
also.
exported
Like
also. Like
if you want
if you
to
want
be solved
to
in
be
other
solved in other
softwares like
softwares like
Nasta,
Nasta,
Nisa,
Nisa,
Mark,
Mark,
Hypermesh,
Hypermesh,
ANSYS,
ANSYS.
even you can
Even you
export
can
it to
export
other
it to other
softwares
softwares
that mesh
that
AutoCAD
mesh
also.
file.
no, no, no.
No. AutoCAD,
Not in AutoCAD
not in
because
AutoCAD
AutoCAD
because
cannot
AutoCAD cannot
have. I don't know
I
if
don't know if
AutoCAD has a
AutoCAD has a
functionality to
functionality to
solve
solve
the
the
simulation
simulation
functionality which is
functionality which is
available in
available in
AutoCAD. Then
AutoCAD.
No,
Then
no.
Autodesk
Autodesk
Inventor,
Inventor,
even
I know
Autodesk Inventor has
Autodesk
the
Inventor has the
functionality
functionality
for
for
analysis. So
analysis.
there we
So
can
there we
export.
can export.
Okay. I was only thinking about the drawing. No?
AutoCAD is
AutoCAD
only
is only
for
for
drawing, sir.
drawing, sir.
Mm-hmm. So
So the
maybe the
Autodesk
drawing.
Inventor is there
Inventor is
where
there where
Autodesk Inventor
Autodesk
has
Inventor
the
has the
functionality of
functionality of
analysis.
analysis.
Yes, yes. So maybe the drawing can be imported.
No, sir.
No, sir.
Okay, okay.
That sketch
That
cannot be
sketch cannot be
imported.
imported.
The CAD
The
model
CAD
can be
model can
imported,
be
sir.
imported, sir.
AutoCAD if
AutoCAD,
it is
if it
having the
is having the
functionality to
functionality to
export the
export
state
the
or
state or
IGS,
IGS,
then
then
yes, in fees we
in
can
fees we
import.
can import.
Okay.
Yes.
Yes.
Any more questions? Correct. So with this, we come to an end of our session number 3 on day 3. I would like to thank both the HS Kushwa sir and Saniket Baisaiker for delivering such a wonderful session, presentation along with an hands-on. So I thank again both of them, and we will be meeting again tomorrow morning at 10:30 a.m. With the same Google Meet link, and we have the same experts, CHS Kushwa sir and Aniket Baisaiker, who will be delivering tomorrow's session. So I thank everybody for attending and joining us for this particular session. Thank you, sir.
Thank you, sir.
Thank you, sir.
I think Kushwa sir mic is muted. So
Yes, yes,
Yes,
yes.
yes, yes.
I'll just check.
I'll just check.
हॅलो. हो चालू सर, कारण झालेलंच आहे आपल्याला. ओके. हो 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 चालतं. ओके सर, थँक्यू सर. हो चालतं सर, बाय सर. हॅलो. हां 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 बोलतो. ते ओके, हां बोला. हो हो मीच करेल पे, काही इश्यू नाही आहे. तर एक मिनिट, माझ्याकडे आहे बहुतेक तरी. एक सेकंड थांबा, आत्ताच करतो. थांबा लाईनवरतीच थांबा. नोव्हेंबरचं दाखवतं. हे नोव्हेंबरचं आहे ना पेमेंट? लास्ट पेड, हां ठीक आहे. बरोबर. आपल्याला किती 2426 करायचं ना? किती? 2507. एक सेकंड ना. 25 2507 ना? 2507 आहे ना? ओके. म्हणून अकाउंट नंबर जर एकदा चेक करता, 4020 CDE W446289. ओके ठीक आहे, डन. मी तुम्हाला हे गुगल आणि फोन पे वरून करतो. हो म्हणजे जनरली मी सगळं फोन पे वरूनच करतो, म्हणजे हे पहिल्यापासून. हे मी तुम्हाला स्क्रीनशॉट, हां ते बरं एक मिनिट, पे करतो आधी. एकच मिनिट, होतं इथे.